Okay, chemical bonding 2, molecular shapes, valence bond theory, molecular orbital theory. So we're going to look at a theory that helps us to predict molecular shapes, and then we'll look at 2 bonding theories that are more advanced. Now, I skipped section 11.1. I've already wasted enough time, so I'm not going to explain why. Read it, it's very interesting. Here we are in 2, VSEPR theory. So VSEPR stands for valence shell electron pair repulsion, VSEPR, which is a mouthful, and so even though it's not really pronounced, you can't pronounce that, but we just say VSEPR, it's close enough. VSEPR theory. So this is based on the idea that electron groups repel each other. It's a very simple model for molecular shapes, but it works pretty well. So the first thing we have to get clear is we're talking about electron groups repelling each other. What do we define as an electron group? An electron group is a lone pair, a single bond, a double bond, a triple bond, or a single electron. So a triple bond has 6 electrons in it. It's 3 pairs of electrons, but it's 1 group of electrons. Okay? A double bond is 1 group. A single bond is 1 group. A lone pair is 1 group. A single electron is even considered 1 group. We won't run into those, but it would be considered a group. So the repulsion between electron groups on interior atoms, not on the terminal ones, but on the interior ones, are what determines the geometry. So if we look at this illustration here, we have a central atom, and this one happens to have 3 electron groups on it. It'd probably be 3 single bonds, and those groups repel each other. And so they're going to spread out in space to have as much space as possible. And it's that repulsion that determines what the shape is. So the preferred geometry has a maximum separation of electron groups because that gives us a minimum energy. So we'll look at different numbers of electron groups. So first off is 2 electron groups, because 1 electron group is nothing, it's boring. It's just a diatomic molecule, and there's no options there. So this says draw the Lewis structure for BeCl2. Well, probably put beryllium in the middle and a chlorine on each side. And here you're getting a little review in how to draw Lewis structures. Skeleton structure, and then we have to figure out how many valence electrons. How many valence electrons does beryllium have? 2. Oops, not that fat 2, just a regular 2. And we have 2 chlorines, and they each have 7 valence electrons. So that's 14 and 2 is 16. And again, on the exam, use your calculator and get the number right. So 16 valence electrons, I've got 2, 4, 6, 8, 10, 12, 14, 16. So the octet rule says we would need to make multiple bonds and do some sharing. But what's special about beryllium? Beryllium often is okay with an incomplete octet. So how can we tell if we should do the octet or not with beryllium? Because sometimes it does an octet. Starts with an F. Formal charges. Well, look at the formal charges, right? So the formal charge, we're going to think about, well, how many electrons did chlorine bring to the molecule? So the chlorine brought 7, it would leave with 7 because it gets its lone pairs in half of the bond here. And the beryl, that's a 0 formal charge. Beryllium brought 2 electrons, and it would leave with 2. It would get half of each of these bonds, and so it's also 0 formal charge. So we're not going to try to do the octet rule here. We're going to leave it alone.
Now, if it wasn't a 0 formal charge, that's what you want to try to get.
Yeah, so if we had non-zero formal charges, then we would look at moving things around, possibly making multiple bonds to see if we could get lower formal charges. Yeah. So that might be useful on the exam. Okay, so now what we're going to do is we're going to look at that central atom, here the beryllium, and ask ourselves how many electron groups are attached to it. 2. Yeah, it is just counting 1, 2. A single bond is a group, and this single bond is a group, 2 groups. So here we have the Earth, right? Beryllium is the Earth today. And this is you, and this is the worst X you've ever had, right? There might be more than one, just pick the worst one in your memory. And so you both have to stay on the planet, but you want to get as far away from that person as possible. They're on one side of the Earth, you're on the other side. You can't get any further, right? So that's what these 2 groups are going to do. They're going to be on opposite sides of the central atom. That make sense? I mean, repulsion. They're repulsive. Just ugh. So we can look at a bond angle here. And the bond angle is always between the bonds with the central atom as the apex? The vertex? What is the name of that? The point of an angle? Vertex? Yeah. I know how to do math, I just don't always remember the words for math. Anyway, this is the angle, it's 180 degrees. So that's what VSEPR theory predicts for this compound, and it's confirmed by observation. And so all of these shapes have names, and this one's called linear because they're in a line. We're not trying to be tricky here, really. Let's look at another one, carbon dioxide. Draw the Lewis structure for carbon dioxide. Well, we have carbon and 2 oxygens. And there's 2 oxygens, they each have 6 electrons, and 4 for the carbon, 12 and 4, 16. So I've got 2, 4, 6, 8, 10, 12, 14, 16. Not an octet. And I don't have beryllium or boron that is going to be good with an incomplete octet, so here I do have to go for filling up the octets. So I need to do some more sharing, take an electron pair there and move them over. Not quite good enough, so I'll move this one over. And now I have 8 electrons on each atom, and if I count formal charges, they are all 0. So there's my Lewis structure. And then to determine its shape, I'm going to look at the central atom and ask myself, how many electron groups? 2. A double bond is 1 group. This double bond is 1 group. And so there's 2 groups. How do 2 things get away from each other? They get on opposite sides of the central atom. And so this is also linear with a bond angle of 180 degrees. Any questions? Let me show you real quick why a double bond is a single group. So here I have a ball and stick model of carbon dioxide, like how I just have that sitting under the sink. So there's the carbon and there's the double bond of the oxygen. These bonds, they may not like each other, but they can't move away from each other because they're between the same 2 atoms, right? And the double bonds here, they're stuck together, so they can't get away from each other. So a multiple bond, whether it's a double or a triple, counts as 1 group. Draw the Lewis structure for BF3. Well, boron and fluorine, and there's 3 of them, so stick them around. And boron has 3 valence electrons and 3 nitrogens with 7 is 24 valence electrons. And for the bonds, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Do I need to make a multiple bond to give everyone an octet? Who's in the middle there? Boron. Boron and beryllium are those little guys that will do an incomplete octet. So before I go making double bonds, I want to check formal charges. And this is not about doing formal charges. So I'm just going to say if you check them, they'll be 0 that way. So this is the correct Lewis structure for BF3. So if we look at the central atom, we ask ourselves, well, how many electron groups are attached to the boron? These aren't trick questions. Three single bonds, right? Well, how do three things get away from each other? Well, if you imagine this is the Earth and maybe you and two X's, I don't know, three people trying to get away from each other. If these two are across from each other, then this one's close, right? So the best we can do is 120 degrees. So we're going for maximum angle of separation. So three things would make this shape. 3 points define a plane, and this is going to be in a plane, and so this makes the shape of a triangle. I think we can all see that, right? Nice triangle. So it's a triangle, and it's a plane, so we call it trigonal planar. Any questions?
So it's the bonds that are repelling each other here, not the atoms that they're attached.
Correct. It's the bonds. It's the electron groups. Because we'll find even a lone pair with no atom on the end will still be repulsive. In fact, it's more repulsive than a bond. Here's another one. Here's formaldehyde. We did the Lewis structure of this one last week or sometime. So here I have a carbon, single bonds to hydrogen, double bond to oxygen. How many electron groups? 3. It kind of says up here formaldehyde also has 3 groups. But there's 3 groups. Single bond, double bond. 3 groups. 3 groups are going to spread out and make a triangle. So here we have an illustration of that. Here's the carbon, double bonded to the oxygen, these 2 hydrogens. The angles here are not perfect, though. They're not exactly 120, because that double bond is a little more repulsive than the single bonds. And so these single bonds here are like, well, you're not as horrible as that one, so I'm willing to get a smidge closer to you so I can get a little further away from that one. So this bond angle in formaldehyde is 116.2, which is a little less than 120. Right, so this is less than 120. Dang it. Less than 120. And these bonds are greater than 120. I do not expect you to remember the bond angles for formaldehyde, but I do want you to be able to predict that these bonds are going to have an angle slightly bigger than 120, and these will be slightly smaller. Yeah?
Is that partly because oxygen has excess valence electrons? They have the 2 on both sides.
It doesn't actually have really anything to do with the oxygen. It's the fact that it's a double bond. So there's single bond, double bond. The double bond is more repulsive than the single bond. The atom at the end doesn't actually matter at this point. So the different types of electron groups have slightly different repulsions. Okay, conceptual problem. A central atom in a 3-atom molecule forms 2 double bonds and has no lone pairs. What's the geometry of the molecule? Linear. Well, how do we know that? Well, we see 2 double bonds. Each double bond is a group. That's 2 groups. And it says there's nothing else going on. 2 groups is linear. So that might work for you. Or you might want to just draw yourself a picture. So here's a double bond. And there's a double bond. And then you say, well, there's 2 groups, right? 2 groups, linear. Any questions? Are 3-atom molecules always going to be trigonal planar? No, they're not.
Are they always going to be?
Oh, the 3-atom ones. Actually, no. I was thinking 3 bonds, but no, 3 atoms like that. We'll find out are not always.
Is that because some are just less repulsed by others?
It's because of lone pairs. Yeah, lone pairs, those stealthy guys. So here's 2 groups, here's 3 groups, and here's the balloons. And so the balloons can help us understand and visualize what's going on with the repulsion here. These two are easy because they're in a plane, and so we draw them on the screen, and they're not really confusing at all. When things get three-dimensional, then your eyes start playing tricks on you, and you're not sure what you're seeing. If we tie two balloons together, they will do this, so, be opposite of each other. And if we put a third balloon in there, it'll squish those two closer together. And then we'll see what happens when we put a fourth balloon in there. But for this balloon analogy, it's important to note that the balloons represent electron groups, not atoms. They're electron groups. So adding the fourth balloon makes this a three-dimensional object, causes those other three balloons to be squished a little closer together. And now what we have is four things spread evenly in three-dimensional space. And I'm sure at some point in my schooling I learned how to do this. I don't remember. But I do know that the angle is 109.5. So this is called a tetrahedron. It's a polygon that has four corners. So tetra means four. We have four electron groups. It makes a tetrahedron. The tetrahedron has four identical faces. They're right triangles, equilateral triangles. That's four. Four makes a tetrahedron. So when we have four electron groups, and they're trying to get away from each other, they'll make a tetrahedron. So methane is a molecule that does this. Here's its Lewis structure. We look at the carbon in the middle, and there's four single bonds. That's four groups. Four balloons make a tetrahedron. Four electron groups make a tetrahedron. And so this is a ball and stick model of the methane molecule, and we see that the bond angles are 109.5. This looks flat, and when we draw Lewis structures, they are flat, and it's much easier to draw that way. But this is a 90-degree angle, right? And they can get further away than that. They can do 109.5. So let's look at this one. What is the geometry of the HCN molecule? And the Lewis structure is given here. Linear. What we're asking ourselves is, how many electron groups on the central atom? Well, the triple bond is one group, and the single bond is one group. Two groups? Linear. Any questions? Well, what if we stick a fifth thing in there? So in this 5-balloon shape, this is called a trigonal bipyramid. Because if we look at this shape, there's a triangle here in the middle, and then there's a pyramid up here, and there's a second pyramid down here. So it's triangular, and it's got pyramids, and there's two pyramids. Trigonal bipyramid. The thing about this shape that's kind of unusual is that the bond angles are not all the same. You can't spread 5 things out evenly in space. Like, wait a minute, why? Well, you can't. This is the best you can do. So we've got what are called the axial groups. So if we put those straight up and down like the axis of the Earth, and then we have the equatorial groups, these would be around the axis. And so the way I think of this is, here's a little girl, she's got, little curl, and here's her body, and maybe she's on point or something, as her legs, and she's got her arms down by her sides or something. Behind her back, so you can't see. And this is her tutu. Okay? I know it's like a black scribble, but you get the idea? And these are different because the angle between her head and her tutu is 90 degrees. And between the tutu and her legs is 90 degrees. But the angle between these groups that are in the equatorial position in the tutu, those are 120 degrees. Anybody have any questions about that?
Are we going to need to know all of these angles?
You will need to know these angles. And we've covered all the angles. There's 180 degrees, there's 120 degrees, there's 90 degrees, and then the one weird one is 109.5. Any of the other angles, I just expect you to know bigger than or smaller than, okay? Because they're going to be different for every molecule. So a molecule like phosphorus pentachloride would do this. You can only have a trigonal bipyramid if you have a larger central atom that can expand its octet, because this is an expanded octet. And then an octahedral geometry. So we add a sixth balloon, and we get this octahedral geometry. So now the shape, I suppose we could call it a square bipyramid, but we don't. We just call it an octahedron. So it has 8 sides. Something like sulfur hexafluoride will do this. And when we look here at angles, now we see that all the angles are the same again. We have 90 degrees and 90 degrees. Everywhere's 90 degrees. But we can still think about the little girl, like, and here's her tutu. Right? It's just now that she has 4 balloons in there instead of 3. Any questions? Yes?
Couldn't you turn it on its side and still have the same?
Yes. This one, because all the bond angles are the same, we can turn it on its side and it's exactly the same. So this balloon octahedron, I have red balloons, and we can still talk about these as axial and these as equatorial. But I can turn it on its side, and these two can be axial, and now she's got a striped tutu. We can't do that with the trigonal bipyramid. Because if I try to put any of the other two, they're not across from each other, right? So these structures are similar, and yet they're different. Any other questions? Oh, I thought I paused, but I didn't. Okay. Determine the molecular geometry of CCl4. Geometry is determined by electron groups on the central atom. Got to start with the Lewis structure. So carbon in the middle, chlorines around it. Our Lewis structures are always flat. And then we would count up the number of electrons, and I will just cut to the end. And all of these guys are going to have octets. And so there's the finished Lewis structure. How many electron groups around the carbon? 4. 4 electron groups. So what's the geometry? Tetrahedral. The good thing about questions like this on an exam is they're going to be multiple choice. And so if you don't know how to spell tetrahedral or you don't know how to pronounce tetrahedral, you can still pick it out of a list, right? Tetra means 4. So how would we draw this? What would this look like? Well, we'll talk more about this a little bit later. But we put as much of it in the plane of the screen as we can, and then this one's going to kind of be sticking out at us, and this one is going to be in the back, and we can kind of see where it attaches. We can also do this with wedges. And so we use a solid wedge coming out to indicate this one's jumping out at you, and then a hatched or a dashed wedge to indicate that it's behind the screen, like if you can't see it. So, tetrahedral geometry. Any questions?